welcome back. Let me ask you something. If you walk up the stairs nice and slow, like this guy, and then you run up the stairs twice as fast, like this guy, what's the difference in how much work is done? Work, if we remember, is force times distance. There is no time component. In both cases, we've traveled the same distance, we've carried the same weight, which is ourselves, so the same work is done. A job done faster is the same amount of work done. Faster work doesn't mean more work, it means more power. Okay, so power is the rate of work done, or work per unit of time. We can also express it in terms of, since work is a transfer of energy, we can express it as energy per unit of time. The unit for work is the watt, where 1 watt is 1 joule per second. We can also express it in other units. We can use larger units, gigawatts, megawatts, kilowatts, to represent billion, million, and 1,000 watts, respectively. These are, of course, standard SI units. So let's give an example of how this works. If we have an elevator and its occupants with a mass of 1,300 kilograms, the elevator motor lifts the elevator to the 12th floor, a distance of about 40 meters, and the time it takes is 75 seconds. Okay, so we have the mass, we have the distance, and we have the time. What's the average power output of the elevator motor? Well, let's work through the solution. Power, we said, was work over time. The work done is, in this case, since we're lifting something upwards, mass times gravity times the change in height, and the power is work over time, so mgh over t. So all we have to do at this point is plug in our values for the mass, for gravity, gravitational field strength of 9.8, the height in meters, and the time in seconds, and that will give us our final power output of, wow, 6,794.7 watts. Okay, so that's pretty powerful. So let's do another example. If we have a tractor pulling a plow, and the tractor is able to exert a force of 7,500 newtons over a distance of 3.2 kilometers, and we know that the output of the tractor is 25 kilowatts, how quickly or how long does it take for that tractor to do the work? So, what I want you to do is I want you to pause the video for a second and see if you can work that out, and when you're done you can click continue. I'll just kind of stand here and wait. Sorry, I just went to get a coffee. All right, so let's look at the solution. Power, we said, is work over time. So we can rearrange that equation to time is work over power. And in this case, the work done is force times distance. We're not lifting anything, so we don't have to use mgh. We're going to go back to our force times distance formula for work. And so our time is simply force times distance over power. And then we plug in our values, 7,500 newtons times the distance in meters. Okay, we're not going to use kilometers now, we're going to use meters, go back to standard units, 3,200 meters divided by 25,000 watts, and we find that it takes about 960 seconds, which is 16 minutes. So let's go back to how we started with running upstairs. Suppose hypothetically that I challenge a student to a race up the stairs. Now here are the stats. Okay, so I have a mass of about 90 kilograms and the student has a mass of 65 kilograms. So we race up the stairs, it takes me about 9.46 seconds and the student creams me 7.8 seconds, right? So almost a second and a half faster. No contest, really. But what about power output? Okay, so let's look at my power output. Power is work over time. In this case, the work done, remember, the work done is going to be mgh, and the time is 9.46 seconds. So my mass times 9.8 times the height. So running up 2 flights of stairs is about 8 meters, right? So the power output is 746 watts. Now, how about the student? So the student, the power, again, work over time, mgh. So the student's mass is 65 kilograms times 9.8 times 8 over the time, which is 7.8 seconds. And we have 653 watts. Okay? So even though the student is a lot faster than me, I have more power output. Now, this number 646 watts is kind of interesting because that's actually an old unit of power. Well, old unit, it's still quite used quite frequently, but it's not an SI unit, it's an imperial unit, and that is the horsepower. So the horsepower is 745.7 watts, and that represents the amount of power that a horse can output for an extended period of time, right? So this is not a horse running at full gallop. This is a horse doing work all day long, pulling a plow or whatever, can do about 745.7 watts. So at my maximum, I can output about 1 horsepower, whereas the horse can output that power all day long.